Welcome to problem 645, Smith Van Ness, 8th edition. So this is a pretty long problem. It involves a lot of calculations, but it covers just about all the material that we've covered in chapter 6. So I want to go through this and make sure you understand how things are done and make sure you can do calculations like this for quizzes and exams. So in this problem, the first part of the question says, from data in the steam table, so we're working with water, determine the values for GL and GV, the Gibbs free energy, the Gibbs energy of the liquid and vapor phase for saturated liquid and vapor at 1000 kilopascals. Should these be the same? Then they want us to calculate delta H of vaporization over temperature and delta S of vaporization at temperature. Then they want us to do residual value calculations, and then they want us to do some equations with or calculations with the Clapeyron equation. The last part, which we're going to skip right now, we're going to skip that for now. It says apply appropriate generalized correlation for evaluation of VR, HR, and SR for saturated vapor. We'll do that later with some other materials. So anyway, in this problem, let's look at the first part. The first part is calculate the Gibbs energy for both the saturated liquid and vapor phase at 1000 kilopascals, and we're to say whether or not we expect these values to be the same. And so the first part of the question, or actually the second part of the question, is the easiest part of the question if you've been keeping up with the material in this chapter, and the answer should be yes. The Gibbs free energy, the Gibbs energy of a liquid phase and vapor phase in equilibrium by definition are equal to each other. And so that's something that you should realize right away when you're looking at this problem. And as I note here, you're going to use this concept over and over in your second semester thermodynamics book. So thermodynamics course. So make sure that you get that embedded in your mind. So if we go to the steam tables, though, you'll notice you don't have a Gibbs free energy entry. And maybe some steam tables do, but online, but our textbook certainly doesn't. So how do we get that? Well, we just use the definition of Gibbs free energy. And Gibbs free energy is G is equal to H minus TS. So all I have to do then is look up values of H and S, and we can calculate what G is. And so you should be looking that up now. We're at a pressure of 1000 kilopascals. And so we can look up the values of HT and S and on page 703 in your steam tables. And so I've got some values ready here. Saturated liquid, enthalpy and entropy, saturated vapor, the temperature. One of the things you got to remember for this temperature here, we have to use Kelvin. Thermodynamics, you should use Kelvin every time you do a temperature calculation, especially if it involves the second law of thermodynamics. We have to use absolute temperature, Kelvin or Rankine, if we're going to deal with American engineering units. So anyway, we now have our values that are written down, and again, be very careful as you read these values out. Make sure you get the right units set with them, and we can just go ahead and we can calculate the Gibbs free energy of the vapor phase is minus 206 kilojoules per kilogram. We do the same calculation for the liquid phase, and we get the same value. Now, granted, they're a couple of decimal points off, but this is less than 1%. For all practical purposes, these values are exactly the same. Remember that the steam table values that you see were derived from experimental conditions, experimental measurements. Typically, if you're doing really good work in a lab, you're going to see about 5% relative standard deviation or standard error in your measurements, and these values are definitely within that limit. So yes, we get the values that we expected. The Gibbs energy of liquid and vapor in equilibrium are the same. So in part B, what they want us to do is they want us to determine delta H and delta S of vaporization. And so we can do that. This is just a basically delta H of vaporization over T compared to delta S of vaporization. And so again, we don't have to do any interpolation or anything like that. We just go to our steam tables, we look up what we've already got, what our delta or what our H values are, our S values are. We just calculate the delta, and then we compare delta H of vaporization over T. Remember, again, this has to be Kelvin. And then delta S of vaporization, you can see that these are exactly the same values. And this is exactly what the Clapeyron equation 684 in your textbook on page 236 tells you should be. So we've verified that. Get rid of that. Part C. So part C is where this is the first residual value calculation that we're going to do in this course, and we are going to use the steam tables for this. And so what we are asked to do is find the residual values of volume, enthalpy, and entropy for saturated vapor at 1,000 kilopascals. So remember that residual value is the real value minus the value it would be as an ideal gas. In this case, for the real values, we have the steam tables. Right? We don't need to use the generalized correlations, which is what your problem asked you to do at the very end, and we're going to skip that for now. So for the real values, we're going to use the steam tables. For the ideal gas values, we're going to use the ideal gas values. So let's assemble the real properties first. So the real properties first, and again, these are just looking up values in the steam tables. And so I'm just going to copy those again. We've already got them up here, but I'm just going to rename them as real in this case, just so that our residual calculation is a little more plain. And so I even did this. I don't think we actually need this, but I even calculated the real gives free energy that we have up there. And then I also added in the real volume. This is the real specific volume of the saturated vapor at 1,000 kilopascals. So we've got all our real values. Now we can start calculating ideal gas properties. And the easiest one to do would be for the volume, right? So the volume is PV equals RT. And so V is just RT divided by P. And so we can plug our values of pressure and temperature, or temperature in, and we get a volume in molar terms. And then since our steam tables are in mass terms, on a mass basis, we divide through by the molecular weight of water. I was using 18 grams per mole for water. And so you can see we've got a little bit of a difference. And so the residual value for volume is going to be about 15 cubic centimeters per gram, or cubic centimeter is about a mil. So 1 milliliter. And what you'll notice is that our real volume, 194.3, our ideal gas volume, 209, our real volume is always smaller than the ideal gas, and this is because this is just a property of real molecules. There's net attractive force, especially with something that hydrogen bonds so strongly as water. So our residual value is about minus 15 cubic centimeters per gram. So that was the easy part. A little more difficult conceptually is how do we calculate the ideal gas values of enthalpy and entropy for steam? And if you remember back from either chemistry or your material and energy balance courses, we're going to need some kind of a reference state for this. And so what you can do And some of this uses a little hindsight. You may not, hopefully this will be a little more obvious to you after we go through it. This may not be obvious the first time you go through this. But our steam is at, I'm just going to say 180 degrees Celsius, right? And the pressure is at 1,000 kilopascals. We want to treat this, we want to see what this would be like as an ideal gas. So think back to an ideal gas definition and what we said the range of conditions were where the ideal gas law was most valid. We really didn't talk about temperature very much. When we mentioned ideal gases, what property were we usually talking about as far as that range being restricted for the ideal gas being valid? Well, that was pressure. So the ideal gas law is more valid when the pressure is very low. So what we can do, and hopefully later you'll see why this is especially convenient. What we can do is we can keep the temperature the same, so about 180 degrees C, but now we're going to go to a very low pressure, and we're going to look up the enthalpy and entropy values at that 180 degrees C and a very low pressure, and then we're going to go from there. So if I go to my steam tables in the back of my book and I look up what's the lowest pressure entry I have. Well, the lowest pressure entry I have is 1 kilopascal. 1 kilopascal, and that will be on, let's see, page 690, page 692. You see on the left column, 1 kilopascal, 10, 20, 30. And you'll see that you have temperature entries of 75, 100, 125, 150, 175, 200 degrees C. So what we're going to have to do then is we're going to say, okay, let's look up the enthalpy and the entropy at 1 kilopascal and 179.73 degrees C, which is what our temperature is. Or what's that? Sorry, that I had a round off. That should be 0.88 degrees in units degrees C. All right, so we have to do that with interpolation because your steam tables don't have an entry at 179.88. And so this is the interpolation for enthalpy at that condition. So x value or x coordinate is or independent is temperature. M is the enthalpy. And so the enthalpy of steam at 1 kilopascal and 179.88 degrees C is 2841 kilojoules per kilogram. The thing to realize, remember, for an ideal gas, enthalpy is a function of temperature only. All right. So we've got, this is the ideal gas enthalpy at our temperature, about 180 degrees C, but at a lower pressure. If we were to take the pressure, if we were to take this gas at 1 kilopascal and 180 degrees C, and we were to increase the pressure to 1,000 kilopascals, how would our enthalpy change? Well, it shouldn't change at all. It won't change. For an ideal gas, remember, delta H is equal to the integral of Cp dt. If temperature doesn't change, delta H is 0. And so this enthalpy right here, this is the enthalpy of steam at 1 kilopascal and 180 degrees C. It's also the enthalpy of steam at 180 degrees C and any other pressure you can think of, as long as you're assuming it's an ideal gas. So what that means is that for the enthalpy calculation of an ideal gas, we're done. This is our enthalpy of our ideal gas. So hold that thought for a while, and now let's go to the entropy. So the entropy calculation, this is the entropy interpolation. So all we're doing is interpolating to find the entropy at 1 kilopascal and about 180 degrees C. And you can see we get a value of 9.883 kilojoules per kilogram Kelvin. Unlike enthalpy, though, we're not done with this entropy value yet. Right? We have to realize that the entropy of an ideal gas is also a function of pressure as well as temperature. If you remember back from chapter 5, delta S for an ideal gas is equal to Cp dt over T minus R log P minus R d log of P. So what we are doing, what we have to do is we have to take this value. Remember, this is at, so let me just add this. This is at 1 kilopascal and 180 degrees C. We need to take this value and we need to translate it to our actual pressure so that we can treat it as an ideal gas at our actual pressure. So we need to go from P0 of 1 kilopascal right here to a pressure of 1,000 kilopascals. And we just use the equation that we had back from chapter 5. We integrate to get delta S. And so what I've done, you can go through and you can do the integration yourself, but temperature is not changing. So the Cp dt over T term just goes away. All we're left with is a pressure term. And so this is our 1 kilopascal, this is our 1,000 kilopascals, R is our ideal gas constant, the minus sign. And then this is our value up here, the 9.883 kilojoules per kilogram. And what I've done is I've converted everything to moles because R is the ideal gas constant, which is 8.314 joules per mole Kelvin. So I go through, I get that calculation as 0.12 kilojoules per mole Kelvin. If I convert it back to mass basis by dividing by the molecular weight of water, I get 6.693 kilojoules per kilogram basis. This value is the value of the ideal gas of steam if we treat it at an ideal gas at 180 degrees C, or 179.88, and a pressure of 1,000 kilopascals. I would say probably for this problem, this part might be the most confusing part for you. So, or at least the kind of the newest twist on what we've been doing. But if you sit back and think about it, maybe go through this a couple times, I think it'll make sense. Delta H, enthalpy didn't have to be adjusted because enthalpy is not a function of pressure, it's only a function of temperature. But entropy is a function of both temperature and pressure. So now we have the real values and the ideal gas values, and we can then just calculate the residual values. And so the residual value for enthalpy is about minus 65 kilojoules per kilogram. The residual value, and again, I'm just putting this, because this was calculated in moles, I'm just converting to mass because our steam table's in mass, and so that's negative 0.11 kilojoules per kilogram Kelvin. Something else you might have thought about as you looked at this problem. So there's another way that you could have calculated the ideal gas value of enthalpy and entropy at these conditions. And so we could have used equations 623 and 624, which is just delta H is equal to Cp dt, and delta S is Cp dt over T minus R log P over P, P2 over P1. The problem with that is that you would still have to define a reference state, so some reference temperature and pressure, and you still would have had to assign reference values of the enthalpy and entropy at that reference state. And maybe you would the choice of this reference state would just be arbitrary, and the choice of the values. You can make them anything you wanted. As long as you do the math right, you get a correct value. And so, you know, among 20 students, as I say here, I could easily expect 20 answers, and they could all be right if they were if they did the integration correctly. And so, while you could have done that, I wouldn't have done that. The easier approach to do this, because we're using STEAM, is just to use the STEAM tables. And so here, again, just reiterating what we did, since we knew, or you should have known, or at least now you know, that enthalpy is a function of temperature only for an ideal gas. We use the same temperature, which is 180 degrees C, but the lowest pressure we could find in our steam tables, which happened to be 1 kilopascal. And then from there, we figured out the H and S for the ideal gas state using the equations from Chapter 3 and Chapter 5. Okay, so that is Part C. Part D looks at another subject, and so that is, they ask you to find dPsat dt at 1,000 kilopascals. And apply the Clapeyron equation to evaluate delta S of vaporization at 1,000 kilopascals, and then compare with the steam table value. So just for reference, the Clapeyron equation, you've got multiple forms of the Clapeyron equation in the derivation on page 236. This is a Clapeyron equation right here. dPsat dt is equal to delta H of vaporization over T times delta V of vaporization. And this is an exact thermodynamic relation. And remember, this was derived by setting the Gibbs free energy of the liquid phase equal to the Gibbs energy of the vapor phase. Now what they want is, they want us to find dPsat dt and then calculate delta S of vaporization. And so if you go up, if you wanted to, you could rederive everything, but if you go up a couple lines above this this equation, you'll see that dPsat dt is equal to delta S of vaporization over delta V of vaporization. And so what they want us to calculate delta S of vaporization. Delta V of vaporization we're going to get from the steam tables. And then dPsat dt we need to find somewhere. Where do we get that? So anyway, this is just taking that equation up there, solving for delta S of vaporization. This is what I said before. We can look up delta V of vaporization. That's fine. That's easy. All right, because no interpolation or anything like that. But what is this dPsat dt? How do we get that? Well, if you remember way back from Chapter 3, this will just be the slope of the vapor-liquid line on a PT diagram. But where do you find a PT diagram? And even if you have a PT diagram, how do you find the slope at 1,000 kilopascals? So what we can do, we've got steam tables, right? We've got the steam tables. They give you a big, long list of Psat and temperatures of steam. And so what I would do then is I would go to my steam tables, and we want to measure the slope of this of Psat versus T at 1,000 kilopascals. And so what you can do is just go to your steam tables and do some curve fitting, do some least squares, linear regression fitting, and get the slope of the line. You could do this in MathCAD. I used to do least squares fitting in MathCAD. It can be done. It's a little awkward, I thought, but you can certainly do that. A lot of times for my my preference is to do curve fitting, as long as I can do it, is to do it in Excel. And so what I've done is, here's my point where I want to measure the slope, and so I've taken at least 2 points above and 2 points below to get a straight to get a graph. And so this is my point at 1,000 kilopascals. So I've got at least 2 points above and 2 points below where I want to measure the slope. If you want, you could extend this even further And I think the book solutions, the publisher solutions only use 1 point above and 1 point below. That's, I mean, that's certainly fine. And as you can see, this is a very straight line anyway. Your steam tables are at enough of a fine grid that most everything should be linear, a linear relationship. But just to be sure, I would use a few more points. So if you're going to use Excel, there are several options. You can do the full, if you install the data analysis add-in, do a Google search for how to do that, and it will give you a set of canned routines that you can use for data analysis, and one of them is called linear regression. I can bring this up, resize. And so if you aren't familiar with that, go to options, and there are add-ins. There are add-ins, and so the analysis tool pack, VBA, solver add-in, you can add those things in. And then when you do the curve fitting, it will give, here's my table of my PT values, choose linear regression. It will give you all these details. I used to know exactly what all these were like, but what you're looking for especially is the R squared, the correlation coefficient. This is the intercept of your line. This is the slope of your line. We're doing a linear regression. And then you can get Excel to generate a plot of your results, and you can get Excel to add a trend line. Add a trend line, and this will give you your slope and your intercept, and so you can use that in your calculation. So that's what I did here. And so my dpsat dt, which is my slope, is about 23.446. Remember, include the units. I then look up the delta V values from my steam tables, and then I can calculate my delta S from this using the Clapeyron equation. So delta S is equal to dpsat dt times delta V of vaporization, and I get about 4.53 kilojoules per kilogram Kelvin. I look at the actual values. Delta S actual is about 4.45, so a little bit of a difference. And again, remember, we're dealing with experimental data. So that's our first problem where we've done some residual value calculations. In this case, we used property tables for our real values. The next problems that we do where we calculate residual values, we're going to use the generalized correlations. So we may pick up the last part of this problem and do this for steam, or we can do it for some other problems where we have carbon dioxide or ethane or methane or some other gas where we want to calculate the residual properties.